Recording's rolling. It is Wednesday, September 24. Last couple of days, last couple of days, you guys have been working on this friction lab and this Atwood lab. So at the beginning of class right now, I do want to debrief these with you guys, show you guys what the ideal answers would look like. Since you guys have been working with these couple of days, you can know if you're on the right track. And then after that, I'll give you guys the rest of class to finish these. So collect all the data you need, make the equations, the graph for the friction lab, and then write it for AP. That worked out like a perfect amount of time my first period class. Tomorrow, tomorrow all day, let's do technical puzzles. I'll be solving those with you guys. So let's start with friction labs. So the left side of the page, you were doing exactly this setup. You're taking your spring scale, some different lab weights, and you were dragging them horizontally across a surface at a constant velocity so that there was zero net force. And what that would mean is that the reading on the spring scale is exactly equal to the friction force. And if you pull horizontally, then the normal force would also be equal to the weight. Okay, so you try a different weight, maybe 1, 2, 5, whatever. And there would be different pulling forces. And then you could graph. Now, I put F pull versus weight, but really, in terms of physics, right, you'd be more interested in friction force versus normal force to match this equation right here. So I'll put it this way. So friction force here, normal force here. And you guys, did you scale your axes? Did you put 0, 0 right at the origin point? And then go, for example, 2, 4, 6, 8, 10 newtons like that. And then you'd be like 1, 2, 3, 4, 5. I didn't scale that right. Well, here, let's scratch that. I'm going to call this 0.5, 1, 1.5, 2.0. I think that'll scale better. Right. And then, okay, you recorded pulling forces for each weight and then took the ratio. Okay. And then I think you ideally would have been getting consistent ratio. And what that would look like on a graph is something kind of like this. Zip. Okay. Did you guys get that? Some of you guys finished this in about straight lines like that. I know because I've been walking around looking at your papers. That is a really good looking graph of this. And you can make an equation with that. You can get the friction force, or I call it the pulling force, but it is the friction force if it's on the block. Okay? So friction force is equal to the slope times the normal force. Isn't that true? Right. Yeah. Whatever the slope is. Because what's the slope you guys got for this? I think some of you guys got like about 0.2. Not everybody, because it depends what surfaces you use. Some of you guys were really careful to wrap your weights in masking tape so that all the surfaces were the same, because otherwise they're a little different. Some of you guys were pulling across the lab table, some of you guys were pulling across the track. Right? So it might not be exactly 0.2, but some of you guys got that. Right? And that would be a constant slope. So that, do you guys see that equation would first of all describe that graph? Is that okay? Mm-hmm. You guys see how it also fits this format exactly? So, you guys just found the coefficient of friction. It's the slope of that line, isn't it? So the mu represents the coefficient of friction. Maybe I should say coefficient of kinetic friction, right? This is fighting. You get that? Okay. And then there was so do you guys go with that first one? Okay. Then there was a different way to also get coefficient of friction. Now this one's more conceptually involved. It's where you take each of these weights one at a time. Maybe you graph them enough, you take control from the materials. You put them on an incline and then change that incline until they naturally slide down at constant velocity. Now, if they're sliding down at constant velocity, that's also an equilibrium example. Okay. And then you can follow this proof. No, guys, this proof right here. I think I walked through this with you guys the other day, and you have this in your thumbnail notes anyway. So you guys have this. You guys know this. Understand this full process. So we've got equilibrium, it's constant velocity. Okay. Eventually, at the end of this, the mass and the gravity field cancel out, so you can calculate coefficient of friction a different way. Now, what did that mean experimentally? And some of you guys did this one, some of you guys are in the middle of doing this, is that you can have different weights, like 1, 2, 5, 10 newtons, whatever. Okay? Do you guys get about the same angle that they would break and slide down at constant velocity, approximately? Maybe you got like 10 degrees and 11 degrees and 13 degrees and 12 degrees, maybe something like that, right? But maybe plus minus a degree, but it should have been approximately the same angle over and over. If I pick kind of in the middle, what's the average of those? Like 11.5 or whatever. And then I told you guys to take the tangent. So here, I'll just do tangent of the average just to have a number. Right? Let's say you had some angle, you took the tangent of that, and you got something like that. Now look at that. Now, since they're all the same, you can put tangent theta for like the y-axis and put different weights on the x-axis. Okay? Of course, you start this at 0 and scale this, blah, blah, blah. Right, let's put like 0.2 up here. Right? And some of these are a little bit above, some of these maybe a little bit low, or maybe they're all exactly the same. Okay? But basically, line of best fit, this should be like a flat line, right? If they're all breaking the same angle, therefore the tangent of the angle is about the same, therefore it's a flat line. You get that? So regardless of the weight, they were all breaking the same angle, and tangent of the angle is about the same. You get that? Okay? And I started an equation for you guys. It's kind of like y equals, except y is tan theta. So it says tan theta equals. Guys, how do you write the equation of a flat line? Isn't it just like, yeah, is it just that value? And my calculator is saying like 0.203 something. So you do like 0.20 something probably that. Right? And how many of you guys made the connection here? Point. Okay, see, it's the same thing, same thing. So mu is tan theta, okay. Or mu sub k is tan theta. Okay, they're the same thing. Right. Okay. Again, been walking around, checking you guys' work. Yeah, been walking around checking you guys' work, and a lot of you guys were getting that. You were getting maybe you got like 0.22 and 0.19 or 0.18 and 0.21, but they're all.
What is the bottom box thing?
It says coefficient of friction mu sub k is tan theta. Okay, which is exactly what this is. This is the bottom box. It's the same thing. Okay. Again, you guys know this because I would not be surprised at all if you got enough RQ in May where they had to do exactly this. Say, oh, you set a weight on an incline and it slides down constant velocity. What's the coefficient of friction? And then you either have to know this or derive it. If it was an FRQ, you would have to start from scratch. Like start from the like set up a free-body diagram and go through all these steps one at a time and show exactly where that comes from. Okay. Did you guys be ready to do that in May? Is it? Okay. Now the other lab, okay, two parts of this. There was what I'm calling a classic Atwood and a modified Atwood. Here we go. Okay. So let's start with the classic Atwood. So how do you guys use different combinations of these lab weights right here, like different masses? And you could determine what was the acceleration, or you're supposed to determine acceleration kinematically. So how far does it move and how much time on the stopwatch starting from rest. So you can calculate the acceleration. And then I'm saying, what would that acceleration be as a function of these input masses, M1 and M2, right? Right. So there's different ways you can determine this through dynamics. Really two main methods. Right? Now, one method involves a system of equations that starts with these two green boxes. Right? So let me start with those just to knock those out of the way. You guys see, if you do perspective of each box, or each mass, do you guys see this mass here has two forces on it? There's the tension up and the weight down. And yeah, that difference would be the net force. You guys see that? This is Newton's second law of motion as it applies only to mass one. F equals ma. So net force equals mass times acceleration. Okay. Then you could do a similar setup for mass 2. This also has two forces. One of them is also results in ma. Okay? You could solve it with a system of equations for those two free boxes. Now, more often than not, when I do Atwoods with you guys, and probably tomorrow if we get to an Atwood tomorrow, I'll actually do what's called a whole system approach, which is to look at this as a giant system. And from a system point of view, this tension is just an internal force that just holds everything together. Kind of like if I'm moving this pen around, I think there's a bunch of little forces between the plastic molecules that are just holding the pen together. That's kind of what this tension is. Okay, so you can just ignore the tension and just focus on the external forces. So, guys, here's Newton's second law of motion. Everybody see this? The resulting acceleration is the net force on the mass. And here would be the net force from a counterclockwise point of view. So, guys, should you add or subtract these two if they're opposing each other? Yeah. Subtract. Okay? So that's the net force. In fact, if they were the same weight, wouldn't that just be 0? And it wouldn't accelerate at all. Okay? But then divide by the total mass, which is the total inertia, and that will give you the acceleration. Okay? If I write that out, again, this is, here, I'll drop down the whole system approach. Okay? I can say the resulting acceleration is the net force on the total mass, which is like the difference in weights over the sum of masses difference in weight because weight is a vector quantity or force is a vector. Sum of mass is always because mass is a scalar. Okay? Guys, could you factor a g out of the top and do difference in masses over sum of masses times the gravity field that's following it? Like that? Okay. That is exactly the answer I'm looking for down in this box. Because this is this answer. Okay? You guys see how I was helping you out with the star columns? So the last star column is the acceleration you calculated kinematically. That's like A. A equals what? Okay. I told you it has something to do with the difference in masses, the sum of the masses, and the gravity field. And then that's it. That's exactly how you arrange it. That's exactly the answer. And if you're looking at your numbers, because you guys are getting experimental data for this, hopefully that aligns pretty closely to your experimental data. Or like fairly close, or like the overall trend. Right. Now there might be a little friction in the wheel that would maybe throw this off a little bit, or something like that. Or maybe this both have a tiny bit of rotational inertia, especially compared to like the little tiny masses, might throw it off a little bit. But otherwise, in the big scheme of things, that's the answer. Okay. And last one is this modified Atwood. Looks like this. Okay. And similar story is we've got two masses, each with their own sets of forces going on. So if I just focus on each individual mass, do you guys see this one has how many forces on it? 2. And that's the setup right here. So the net force results in a mass times acceleration just for that M1. Okay. And this one has, well, maybe at least 3 forces, 4 if I include the friction, although ideally that's negligible. Okay. But these two verticals cancel out. So maybe the net force is the tension, and that results in mass times acceleration for this block, right? Now, again, you could take these 2 green boxes, set up a system of equations, and solve the acceleration that way. You can do that. Okay. But more often than not, I prefer to just do what's called a whole system approach, which is just this gold box right here. So, do you guys see on this whole set of, I see lots of forces flying all over the place, but there's really only one that matters. There's one external force driving the whole system. Guys, what's the only force that's driving the whole system to move? M1G. Yeah, the weight of the hanging block. Nothing else matters because the tension is just internal to the system. It's just holding everything together. Right? It's pulling up on the hanging one as much as it's pulling this one direct. So that's just internal. Okay. These two forces cancel out. So the weight of the horizontal moving block and its normal force cancel out. And this friction is negligible. So that doesn't count either. So the only force driving the whole system is the weight of the hanging block. Do you see that would therefore be the net force on the whole system, which goes right there for net force, doesn't it? You see it? Okay. But how much inertia is being moved around? Isn't it the sum of the masses? Okay. And so that right there is the answer to this box down here. Okay. Again, it helps you out with starred columns. So you calculated acceleration kinematically. So acceleration equals what? I starred the sum of masses, which shows up in the denominator. I starred just mass 1 itself, which is the hanging mass, and the gravity field. Boom, boom. It's all there. You guys see it's all there? Right. So this gold box right here is the answer to this modified Atwood. Right? So all these posters are hanging on my wall. So you have all the answers posted in your thumbnail notes. Okay. So I'll give you guys the rest of the class to finish anything you need to finish. Also, remember do AP style write up and staple this to your lab page and turn that into the grade tray. I will walk around and help you guys out.